thankfully, there is a much simpler way to extract content, which is it's completely statistical and it has nothing to do with trying to parse XML, and it works for a surprisingly wide variety of content on the web. And the idea is that when you have an HTML page, as a search engine, what you're after is you're after a block of text. Right? That block of text is usually the content, right? So in news, you'll have a news story, and then there will be fluff around it. So the general intuition, the big idea, is that the block of content is going to have relatively many words per token, and the stuff around it, the junk, is going to have a lot more tags per token. So you want to latch on to this idea. So basically what you want to do is take a web page. Instead of looking at it as a tree, just linearize it as a sequence of tokens. Now these tokens are going to be of two types. Each token is either going to be a tag or it's going to be a non-tag. And a non-tag is usually just a word that is rendered on the page, and the tag is something that has to do with how it's formatted. So now you have a sequence of tags and non-tags. And what you want to do is you want to find the portion of a web page that seems to have unusually few tags in it. So if you try to show it graphically, basically what you're looking at is you can try to plot the count, the cumulative number of tags against the total number of tokens that you see in the web page. So in this case, it's an HTML page. It has about 3,500 tokens, and what I'm plotting here is the cumulative number of tags. As I walk from token 1, every time I see a tag, where I'm just defining a tag as anything between a less than and a greater than character, anytime I see a tag, I increment the tag count. So if you do something like that, you'll get a graph that looks approximately like this, the bold black line. Right? So it's going to keep going up, but it doesn't go up uniformly. And at some point, at least this is typical for news pages and similarly formatted pages, you'll have a portion of the graph that looks relatively flat. Think about what this means. This means that in this portion, as I'm going from this part to this part, I'm seeing tokens, but very few of these tokens are tags. The tag count doesn't go up. So that's a portion that looks like a portion of plain text. So what you want to do is you want to come up with some method that will be able to identify portions like that, the tag plateaus. And it turns out that for many types of news and similarly formatted pages, that plateau corresponds to the chunk of content that you're trying to extract. So in CNN, that's actually the story, and everything around it is navigation and other junk. So you want to be able to extract those plateaus out of a graph. So how do you do it? Well, formally, you define a page as a sequence. You have n tokens, so x1 through xn. That's a set of variables, one for each token in the page. And what those variables are going to be is I'm going to say that x1 is 1 if the corresponding token is a tag, and it's 0 if it's a non-tag. And what I want is I want to find A and B such that to the left of an A I have lots of tags, to the right of a B I have lots of tags, but in between A and B I have as few tags as possible. The objective function that corresponds to that is this function right there, right? I'm adding up the xi's from the beginning until A. So this counts how many tags I have up until A. The right side is how many tags I have after B, from B until the end of the page. And the part in the middle, that tells me how few tags I have between A and B. So I'm adding up 1 minus xi. So if there was a tag, I'm adding a 0, and if there was a word, a non-tag, I'd be adding a 1. So that overall expression says how many tags do I have on the left, plus how many tags I have on the right, plus how many non-tags I have in the middle. And what you want to do is you want to find A and B such that this quantity is maximized. Right? Now, you'll notice that I have a little constant c here. That constant is the slope of the line. It's the total number of tags divided by the total number of non-tags. Well, it's not the slope, but it's related to the slope. And there is a strong reason why you need it. Right. So for a moment, just suppose that C is not there. Suppose I'm just adding up the number of tags on the left, the number of tags on the right, and the number of non-tags in the middle. Look at this picture and try to figure out which values of A and B would actually maximize that quantity. So the values A and B that I have here, would they maximize the quantity? It looks like they would, but they actually won't. Right. And to see why, what you really want to do is you want to look at the total, you want to look at the absolute value of the numbers on the x and the y-axis. Right? So let's say here I have, when I have about 2,500 tokens, I have a little bit under 800 tags. So what does that tell me? That tells me that for every tag, I have how many non-tags on this page? So 2,500 and a little bit under 800, yes. 3 and a bit. No, it's actually 2 and a bit, right? So that's a total token count. That includes the tags. Right? So for every tag, I'm going to have 2 non-tags. Okay. So now suppose that I start with A's and B's here, where I would want them to be, right? And now suppose I took this A and I moved it a little bit to the left. I'm going to lose some tags in the left portion, and I'm going to gain some non-tags in the middle portion. But the problem is, for every tag I lose, I'm going to gain 2 non-tags. And you should be able to convince yourself that as long as you move A to the right, your total objective function is going to increase. It has to do with a imbalance of tags and non-tags. There's more non-tags, so this objective function, if you don't include the C, it's going to be biased towards A drifting down to 0 and B drifting down to the very end. And those values would actually maximize the value of the objective function. Why? Because overall there's twice as many non-tags as there are tags in this case. So C serves as a way of compensating for that imbalance. Basically it says, okay, however many non-tags you have there, I'm going to convert it to the tag scale. Right? Total number of tags divided by the total number of non-tags. So that makes the increment that I get in the middle comparable to the decrements that I get on the left side and the right side. So it's necessary, if you do it without the C, it'll most often extract the entire page. But if you pick the right C, and it's really just as simple as that, the value that maximizes the objective function, the values of A and B, are going to be those values right there. So it will zero in on the plateau, and then you take the portion of the page between A and B, and that's just going to contain the text that you want to index. So it's a very simple method. It's a lot simpler than writing parsers, and it works for a surprisingly wide variety of domains. Now it has some limitations. It only works for the types of pages where you have a single content section surrounded by navigational junk. But a surprisingly wide number of pages are in that form. And if you wanted to index other pages, there are other similar methods which are statistical, which don't require you to write a parser for every single page that you want to index.